Hello.
Good morning.
Morning. Hello, Jesse. Yeah. All right. So, why don't we get started?
I would like to go, not quite ready, but I'd like to go over the Big Brain HIBALL conference.
Oh, okay. Yeah, that'll be good. We'll do that in a little bit.
There's another one that was like a global. I'm not remembering the name exactly, but it was basically a big EEG meeting that had a lot of really interesting stuff. Let me just pull together my some Slack things from NeuroTechX.
Okay, sounds good. Yeah, thank you. So this week has been interesting. We've had our DevoWorm meeting where we finished up our Summer of Code projects. We had the Hyper Devo Graph, and we had the growing graph neural networks, and they both got submitted. Hussein updated us on some of the stuff he's been doing with medical imaging. He's been doing some pretty nice, medical physics, and he's been doing. There's a channel in the Slack, breast cancer CT, and that's the one he's been posting a lot of updates to. So you might join that if you're interested in that topic. We also covered kind of an aspirational paper on cell modeling using AI, which of course is, it's a sort of a quest in computational biology to kind of find a way to model a cell. And so there was a large group of authors who proposed how we might do that with AI. Interesting but aspirational paper. In the Cognition Futures meeting, we talked about behavior, teleology, and purpose. And this is a classic cybernetics paper by Rosenbluth et al., where they kind of go through sort of the hierarchy of feedback, or how feedback is relevant to, say, generating behavior. And when we talk about behavior, it could be behavior of an agent, it could be behavior of a machine, whatever. Some of that being teleology, some of that being sort of the role of higher order feedback, and so forth. And then, of course, we kind of linked that to the paper we did earlier on 21st century machines, living machines by Bongard and Levin. And then we had our cybernetics meeting where we kind of went through the references for our Evergood regulator theorem paper. So definitely a good set of meetings this week. Let's see. I can go through, I know Morgan's probably not ready yet. I can go through some things from this week that I have. So this week was MetaConnect, and this is an event where they go over their new technologies, their kind of, things that they want to preview that are coming out soon or being released now. So they had a number of consumer products, and then they highlighted this headset that they're working on. This is the Orion AI glasses. So this is something that they debuted at MetaConnect. It's not available to buy yet, but it's like this thing that they're kind of working on, where you can do augmented reality in a pair of glasses that you might wear, and it would be more or less indistinguishable from a pair of glasses that you might wear, walking down the street. So they're using waveguide technology to render the holograms in front of your eyes, and everything is like it hosted in the arms of the glasses, and it's projected outward into your field of view. And then there'd be some puck system that you would hold or put on your belt clip to supply the battery and supply the computation for this. So that's the thing. But the other thing they talked about was this wristband. And this wristband is actually what they consider to be a neural interface. So that's what we'll talk about in a little bit more detail. So the neural interface picks up EMG signals at the wrist, and it translates it into just basically gesture control signals. So you're picking up the muscle activity at the wrist, you're producing gesture signals that you can't necessarily do with hand tracking or eye tracking or some controller, and you're using it in that environment. So it's a very nice technology. I'm not sure how well it works, but one of the things that came out of our discussion on this was that Morgan pointed out that CTRL-Labs was involved in this, in developing this neural wristband. So this is the neural wristband where you have high performance EMG sensors on the wrist. You have this processor that integrates EMG signals to produce input events on device. You have a haptic engine that provides tactile feedback, so it's there's this bidirectional feedback at the surface. Interesting that Morgan brought up CTRL because I wanted to do a little bit of a deep dive into what they've been doing in their history with Meta. So this is an article from, I think, 2019. And so maybe Morgan can tell us a little bit about CTRL-Labs and sort of the background there. But this is where Facebook acquired neural interface startup CTRL-Labs for its mind-reading wristband. And so the deal is reportedly worth between $500 million and $1 billion. And I remember at the time people were criticizing Meta for buying all these companies and spending all this money on VR and AR. And so, but it looks like that is actually bearing fruit now. You're getting this.
We'll see.
Yeah, we'll see.
Yeah,
But still, yeah. Go ahead.
It does go back to it goes back to their VR, right?
Right.
So like this time when they were willing to spend, Lord, it actually just took me a minute to remember that that they were calling it the metaverse.
Oh, right. Yeah.
Yeah. And I don't know if that's my dementia or just how unmemorable that technology was, but it's so control labs is what people call it, and I don't actually remember who are the ones that started it, but our connection with NeuroTechX is that Alexander Bereshon, who I think got some notoriety. I want to say like 2013, like quite a long time ago now, for his performance on a particular Kaggle data set that was like a BCI Kaggle data set, and associated with that, separately from that, actually, he was an EEG researcher in, I think, in New York. That might explain it too, because I think Control Labs is based in New York.
Okay.
Anyway, he had started some sideline projects, a little like the Pi webcam, like eye tracking guy, where he started a project where he was writing interfaces for kind of consumer EEG devices so that you could collect data from yourself. But he was basically doing like how you could do ERP studies with these consumer EEG devices that cost only like $200. And then but it was then like 2017 or something like that. He also started a project called Moab, or the mother of all BCI benchmarks. And that was really like, that was very much like a kind of crowdsourced project on NeuroTechX, or certainly, he used the community to kind of gather data sets and pull together this kind of scikit-learn related project where you were looking at reliability and accuracy of various, mostly motor imagery data sets, but looking across multiple data sets and multiple algorithms, which algorithms were performed the best, right? So kind of dashboard of those. Very, again, like very in line with kind of like a Kaggle like thing, but again, this was like a kind of related to, or very very modeled on scikit-learn as a project. And part of that was that again, like, because he was French, and because the scikit-learn team of French, that like there was a lot of overlap there. and it definitely got a little bit of kind of help and inspiration from NiLearn, or NiLearn, whatever, NiLearn, which was the fMRI machine learning package that from Olivier Roussel and I'm blanking on the big guy. Anyway, it'll come to me. Yes, that's definitely age related. And anyway, so sorry. Just to give you a little backstory in terms of, so like then the other thing is that he was hired. The Moab paper came out. I think he was CTRL-Labs at this point. And he hired in, I think, maybe somebody else that had been involved with Moab. I'll find these in a second, but then we haven't heard from him since. It's like he disappeared.
Yeah.
And as well as there you see these kind of CTRL-Lab demos from like years and years ago, right?
Yeah.
And then just nothing, anyway, might talk a little bit later about open water health, but this is kind of like the same thing. Like, you get these demos and it sounds really promising, but then we don't see anything.
Yeah, it's all like under security, like under NDA or whatever.
And supposedly they're waiting. Like there was one of the kind of metaverse presentations, or supposedly big announcements. Like you got an EMG demo too. But yeah, anyway, so super cool. Looks like there might be a product coming out. It's not dead.
Yeah, well. So one of the big things about this technology is, of course, the movement artifact and getting that calibrated so that it's useful as a control signal. So I mean, is it that you're actually recording the EMG and its components, or you're recording movement artifact and its components? Yeah. And it could be that's somewhat useful, but right, it's not.
It's interesting, right? And it also, it kind of relates to motor control in amputees,
right?
Like you can even when potentially the hand is missing, the there's still enough of the kind of peripheral nerve, or the EMG that is still detectable.
Yeah.
And they're definitely trying to get it. So another thing that's been very popular is, of course, the Minority Report interface. Apparently, that was the first movie to kind of popularize this kind of gestural control or something like that. Anyway, I'm not sure why that movie got so much gets to be the name for this, but they're definitely, though, like I'd heard that they were trying to de-emphasize like your movement. Like you should have to move as little as possible, but still be able to kind of control the, to get the UI kind of interactivity.
Right.
If you see what I mean.
Yeah.
It's like your hand could almost be still, and
right.
But anyway, I think they hit perhaps some, what we academically interesting problems with the with it as well,
right.
Which I would say, I mean, I've said this before, which I would say is true with kind of all of VR. I mean, and that like there's still a really good reason that we're not all strapped in like some early kind of Facebook metaverse, announcement papers and stuff, or demos and things.
Yeah. So Jesse said something about 100% RE demos that remain demos. Yeah, it's like the problem with demos and demo or die is that it's like the demo is not the end of everything, but like sometimes people just kind of get stuck in the demo. And anyways, So continue on. So they bought CTRL-Labs back in 2019. They spent a lot of money on it. People kind of disappeared. Boz, who's the head of AR and VR at Facebook, Andrew Bosworth, talked about kind of how this was going to be like part of the, developing this technology at scale and getting it into consumer products. They actually, in 2019, also published a series of patents around the Myo armband, which is the demo that, I think Morgan was talking about. And this was, of course, developed by North, formerly known as Thalamic Labs. The Myo armband measured electromyography, or they say EEG, it's EMG, to translate muscle activity into gesture-related software inputs. But North moved on from the product and now makes a stylish pair of AR glasses known as Focals. So this is, kind of talking about how you might use a wristband. Bosworth says CTRL-Labs wristband will be instrumental in developing new ways of interacting with machines without needing traditional mouse and keyboard setups, touch screens, or any form of physical controller whatsoever. So this is kind of like why they're doing this. And of course, it's a nice idea, but it's actually, it's interesting that the Apple Vision Pro was released with eye tracking and eye select, so you can use eye tracking to select objects in the environment, and it doesn't actually ship with controllers. So people have been trying to, it works to some extent, and eye tracking, of course, is farther along than this kind of technology. But people are trying to attach eye trackers to their Vision Pro because it's not like the ideal interaction, medium. So, it really depends if, I guess there are two challenges here. One is to get this to work at a good resolution so that it's control that's as seamless as, say, like a controller or a keyboard or whatever, which is not seamless, but you know what I mean. The second is that, will people use this mode of interaction and view it as like equivalent to some other mode of interaction? In other words, could they just pick it up, put it on, and be able to use it like you might use a mouse? and you don't think about using a mouse too much. It's kind of natural to you because we've had them around long enough, and quite frankly, they're actually pretty good at like moving up and down the screen and pointing and clicking. We have that set of interactions in like in neuromuscular control that we have with the mouse. That's going to be the challenge, of course. So yeah, this is definitely something that they're kind of working on to get out into the world. So it's I think farther along than it was, but we'll see. So this is another article here where this is from 2019. This is a bold prediction. Control Labs CEO will have neural interfaces in less than 5 years. So this was Thomas Reardon, the CEO of Control Labs in 2019, talking about how we're going to have these kind of neuromuscular control devices in 5 years. Now it's 5 years today, or right now. So we don't really have that yet, but this is of course the predictions that one makes when you're a tech person, or a tech CEO. So this is basically the sort of the outline of what a neuro control unit looks like. So let me zoom in for people who need to know how this works. So you have you might record from a single muscle, or you're going to have something that's on the outside of the skin. So sometimes in like medical in experiments with animals or in medical settings, they'll insert an electrode near the under subcutaneously near the muscle, or something like that, so they can isolate the muscle. In surface EMG, you put an electrode kind of on where the muscle is, and you try to affix it to the skin so it doesn't fall off, or start recording from another muscle, or get in between the muscles and record movement artifact and things like that. So it's pretty hard to actually get the recording, get the right target place where you want to record from. Then you bring it into a set of signal processing devices. You have this preamp, you have an encoder, you have an oscilloscope, and then you have an oscilloscope and camera, and you can actually basically get this muscle activity, rectify the signal, clean up the signal, and then use it as some control signal for a device. So this is a pretty big challenge. A lot of the signal processing is well known. People know how to do that, to more or less. But the real challenge is understanding what the control aspect is. In other words, what is the sort of threshold for moving your wrist in a certain direction? So you have to really kind of, if you're either moving your wrist or not, that might be a easy problem. But when you're making these movements that are kind of gradual, or you're making these subtle movements, and especially in the hand muscles because they're not that big, it's hard to know kind of, if you want to say recognize certain hand movements or hand gestures, that's a lot harder problem. And knowing what that signal should look like, and selecting that signal and segmenting it out of this time series, out of the trace, that's the thing that you really have to work on and get to. But also recording from the right site. So having a device that will fit and conform to the hand and the wrist and things like that. So this is definitely, again, a big challenge. They have a lot of good people working on it, and it's, really one of these interaction modalities that is up and coming. So we'll see how this works out. And so this is an article in 2021. So this is another research prototype, human-computer interaction at the wrist. So this is a meta press release where they talk about this wrist-based interaction for the next computing platform. And so this is where they're kind of talking about how, why the wrist. So there are many other input sources available, all of them useful. Voice is intuitive, but not private enough for the public sphere, or reliable enough due to background noise. A separate device you could store in your pocket, like a phone or a game controller, adds a layer of friction between you and your environment. In other words, you have to pick it up and use it. And you have to, if you're in, like, say, AR or VR, you have to coordinate that device with the other device you're wearing on your head. So it's hard to kind of remove all that friction. VR in general, it has a lot of friction because you're trying to coordinate kind of this headset, and then you are coordinating devices, and you're trying to align your body to the world, and you're trying to bring up things in your field of view, and there's a lot of friction in modern design, especially like what Meta's been doing in terms of their platform. There's just a lot of friction by nature in VR, and so this is something we want to reduce as much as possible. As we explored the possibilities, placing an input device at the wrist became the clear answer. The wrist is a traditional place to wear a watch, meaning it could reasonably fit into everyday life and social contexts. In other words, people are used to, well, I don't know how much people wear watches anymore, but, people have that metaphor of wearing a wristwatch, checking their wrist, having something on their wrist. It's not like something weird that you wouldn't know how to deal with, because people know kind of how to deal with a wristwatch. Um, and you can use it in everyday life and social contexts. You don't have a sensor sticking out the right side of your head and, you know, looking like a brain slug or something. So it's not jarring to people, I guess. I don't know. Anyways, that the idea is that it's kind of like this social affordance. It's this physical affordance. It's not obtrusive, and it reduces the friction in the environment. And so, wrist-based wearable has the additional benefit of easily serving as a platform for compute, battery, and antennas, while supporting a broad array of sensors. The missing piece was finding a clear path to rich input, and the potentially ideal solution was EMG, which they talk about here. The signals through the wrist are so clear that EMG can understand finger motion of just a millimeter. So if you move your fingers, you notice that at your wrist, sometimes they're like these. It kind of moves. You can feel some movement at the wrist, and that's because you have tendons and muscle that are connected through the hand. So you can actually pick up finger motions through the wrist. And so if you're recording from those muscles, you can get that signal. Now, that doesn't mean that it's easy to acquire. It just means that you can do it. This means that input can be effortless. Ultimately, it may be possible to sense just the intention to move a finger. And this is, of course, coordinating this with some of the things we do in brain-machine interfaces, or recording preparatory signals in the premotor cortex and coordinating all of that. So basically, you're recording the output of the peripheral nervous system, specifically the nerves outside the brain that animate your hand and finger muscles. So that's basically, and then there's this whole mind reading thing that people get into. But yeah, this is another EMG demo. This is controlling virtual objects. So you can see that the hand is, you're moving your hand. There's this device on your wrist, and you can actually control things in a virtual environment. You can reach out for things, grab them. Using that signal, the virtual hand will contract as well. And you have this hopefully seamless interaction. Then there's a typing demo where, again, you can type things on a table, and it can be interpreted as typing on a keyboard. So, the fingers are moving to certain locations, and, the system can reconstruct sort of keyboard swipes or keyboard presses. So that's another demo they have. So, these are all kind of, if you're interested in this, you would, there are a number of demos they did back in 2021. So that's yeah. So that's that stuff.
Sorry.
Anyway.
I was trying to remember the company that had, it was basically a stereo camera that sits on the desk. It sits like where your keyboard would, and it's using computer vision.
Okay.
not. I mean, it wasn't quite typing, but it was giving you the gestural. Um,
Yeah, recording the gestural movements. Right? Yeah.
Again, this has to be age-related dementia.
Oh,
Um, um, a lot of those people, that company started Project North Star, which is like an open source VR
yeah.
headset company. Anyway, if you yeah, if I Google them, uh, I'll get the name of that other company, and um, I think they pivoted. I mean, this is just like archaeology of various San Francisco startups. I think they pivoted to take their sensor that previously sat on the desk
Yeah.
and attached it, and then it became a stereo iPad attachment, stereo camera iPad attachment. And and I do remember this. And then Robert Oostenveld at Donders. uh, um, uh, so Robert Oostenveld is the original developer and lead developer of Field Trip, which is pretty widely used EEG, NEG MATLAB analysis package. Um, he had this. He had a demo
Yeah.
of using an iPad and then basically walking around the subject that's got EG on
Right.
and doing like photo stitching to get the electrode position. Basically he makes a by moving the cameras around, he makes a 3D head model and gets the electrode positions on the head.
Wow.
Yeah.
Okay.
And that's, like we're like two companies, three projects away from the original thing, but it just I was like the EMG picking up the hands.
Yeah.
The others have kind of tried to do that same. I want to move my fingers in the air, but then like I'm going to use computer vision or something
Yeah.
to figure out the keyboard or project, using light to project a keyboard onto a surface and then using that. Yeah. Um,
Yeah.
back at this time, it's also good to remember Facebook had an image, like a brain imaging group,
Okay. Well, they
like
did.
like
Okay.
like a full-on high-end uh super fancy brain imaging group that was doing like whole brain near infrared. Like it was doing, I might go as far as say, kind of weird brain imaging. um, yeah. And again, I need to Google. You can see like around that time, um, maybe a bit later, um, we would get these pictures of what their brain imaging room looked like, and because it was near infrared, there were these cool matrix style kind of imaginings where you've got this thing coming down and it's got like like 100 fiber optic cables that are
Yeah.
coming to a helmet and I think it just speaks to like what was going on in the company at that time in terms of just like all this work kind of with the focus of like the ultimate UI, right?
Yeah.
Or ultimate UX,
Yeah.
right?
Right.
Um,
Extreme
uh,
UX.
extreme, yeah, extreme. um, yeah. Anyway, so I still wonder how much this is, or maybe to Jesse's point in the comments, like how much this is just like we've had these technologies sitting, or we've had these guys working in these back rooms for like 10, 5+ years,
Yeah.
um, hey, this, we should roll this out, or again, like I don't know, will we ever see this device,
Yeah.
you
Yeah.
know
Well,
or will we see like one consumer iteration of it, and then it'll,
yeah.
yeah um,
Well, okay. Yeah. So that,
it wouldn't be the first tech tech
fizzle out. Yeah.
yeah.
There's some open science resources I wanted to share. This is from ASAPBio. This is introducing a prototype directory of organizations and initiatives in open scholarly communication. So this is ASAPBio is an organization that champions open science practice, largely in the form of preprints, but other types of open science activity that stresses replication and you know other things that disseminating scientific information. So this is basically this list that they have of different organizations and initiatives. It's one of the things they do, of course, is to sort of create resources to help people navigate the space. Because there are a lot of weird terms if you're just coming into the field, a lot of organizations, and you may not know what they are, so that you can get on board with the whole practice of open science. You don't have to spend a lot of time kind of wondering what things are. We have, all sorts of different things, preprint servers, advocacy organizations, open science organizations, infrastructure like CurveNote, for example, um, different companies, different journals that are involved in or open science oriented, the knowledge commons. So yeah, it's just like a huge list of organizations that do work in this space. This is something that if you're interested in knowing, like if they're doing a certain thing in your area of interest, like Zotero or Zenodo, you can find out what those organizations are, their contact information, and so forth. So they've produced this list. They also have this set of definitions. So for the purposes of determining what organizations and initiatives to include on the list, we define open scholarly communications as any organization or initiative that focuses on improving openness and transparency in the scholarly communications process. This definition encompasses open access to research, but extends well beyond access to include issues such as preprinting, improvements to peer review, curation services, open source infrastructure, research life cycle publishing, and more. So this is something that's useful, I think, for a lot of different people coming into the area. And I think Morgan is ready.
Well, speaking, a couple things that were talked about on the NeuroTechX Slack here. So one is a new Pi EEG, which is like basically, what it sounds like, where somebody's made a shield, EEG shield, so attaches on top of a Pi. That's interesting. I mean, I don't want to say it's like a spin-off from the University of Edinburgh. It seems like it's a student at the University of Edinburgh who has a side gig as this open source hardware developer. But it's really, it's nice. And so let me use this as an opportunity again to um, suggest people join NeuroTechX to catch all this on Slack.
Okay. Yeah.
And the nice, one side benefit of NeuroTechX Slack, we keep our history. Like
Okay.
I'm not sure for how long, but
Yeah.
we still have our history. Um, uh, yes. So lots of things in terms of EG and F news stuff, and apologies. Well, the last week, and this would have been right before last Saturday's meeting, I think. Yeah, Brainbox Initiative is another meeting that is that finished up before our last week meeting, and it's definitely one of the kind of premier meetings where um, people working on new neuromodulation technologies and kind of science are gathered. Um, so Brainbox Initiative, like I'm not sure exactly. They they're an organization, but I think they also have a commercial arm where they sell things, and definitely one of those. Um, I believe they are reselling a TFUS. It's one of these transcranial focused ultrasound systems.
Yeah.
But I think they might resell, TMS systems. So there's the magnetic coils that people use to, induce activity in the brain, um, and other like TES devices, and are a great source of webinars.
Yeah.
Um, like presentations again, like I think to a certain extent because they are it's their business, but in terms of the people that they get to do these presentations, um, Brainbox is great. Like they get they really do get like top people, and um, I know that the first time that I saw a webinar, or I saw a web presentation on focused ultrasounds, it was uh, Leonard is it Pergese, um, the researcher at Donders, and he's now the head of science for this startup here in San Francisco called Nudge, where there seems to be a kind of uh, um, yeah, there's a lot of excitement in the startup world for TFUS. So it seems like there's three companies, not necessarily all based in San Francisco. Well, San Francisco, like down South Bay, and then down in LA. So really interesting technologies, and the nice thing about Brainbox Initiative, and I'll find links. I think they just made all their posters available online, and they definitely will find all their videos on YouTube from the conference. So BBI 24 for Brainbox Initiative. But yeah, the I just so the 8th Big Brain Workshop 2024 happened in Padua, Italy. That's I don't know why I immediately think of Shakespeare, but yeah, and yeah. So big. This is like it's got a hard to remember website for the event, but Big Brain Project is bigbrainproject.org.
Big Brain
And
Project, all in word.
yeah, bigbrainproject.org.
Let me see if I can bring it up here.
Yep. Yep. And so as this, I mean, certainly this is how it started. If you know, just on their webpage, creating the next generation of highly detailed human brain models by building on the big brain.
Oh, right.
So is it? I gotta say, this is lazy naming.
Yeah.
And because I've had to work with this particular company's products, and the company's name is Brain Products, and I just want to say that that's the crappiest search name, right? So it's like if I'm trying to Google stuff for brain products, you know, tech details, it's just like I get all sorts of brain products.
Yeah.
Don't use brain in the name.
Yeah.
Uh, but I got to say that this particular meeting, is all on YouTube. And let me just get as Big Brain Project. And it has been a total masterclass in brain imaging. I mean, the three sets of like big conference video drops happened like this week. So OHBM, which is the biggest human brain mapping conference. So the O is for Organization of Human Brain Mapping. They dropped all their educational days that are kind of pre-conference workshop tutorials kind of thing. You know what I mean?
Yeah. Yeah.
And I thought those were good, right? So that was like, again, they're focused on like one topic was like, eight presentations on surface cortical surface, I forget what they called it, precision imaging or analysis or something like that, like whole brain modeling, whole brain dynamics. Definitely something on kind of EEG. And these are terrific because this is the big meeting for brain imagers, right? So so it was really nice set of both practical, like kind of overview of the technology or kind of the state of the art, as well as kind of overviews of some of the big research topics and overviews of some of the software. And then Big Brain Drop. and again, this kind of started as an extension of Carl Zillis's like Zillis was a neuroanatomist at Jülich, that was I mean, he was doing really fine histology kind of work on brains. I knew him as the guy who was the only person I knew that was doing really good receptor mapping of the brain.
Yeah.
Again, in this kind of um, uh, histology slash pet kind of way, right? Um, and he was always the one pushing it. And in the kind of original brain imaging books that came out in the, I don't want to say the 90s, but like Arthur Toga, Zillis was in there um, with his brain maps, which were slices usually, right? And Big Brain was like, we're gonna do it, and we're gonna do it like they gotten to the point where Ulick was building its own uh, brain slicing technology, right?
Yeah.
So it just kind of reminded me of because the minimal cell workshop was also this week, or videos dropped this week from Ventnor Institute, and it just kind of reminded me of Ventnor building special hardware to do sequencing, right? Uh, 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 in his case, to kind of beat the the big government effort, but um, that was the idea of Big Brain. And then there was a conference. It was like 2018, and it had it was got a weird, I forget. Anyway, it was like Woods Hole, and talking about this particular data set. It was huge, right? So it was like 10 micron resolution, and you could see every cell, and it was this like it was this galaxy, or this like universe view of the brain, right?
Yeah.
Where you could kind of endlessly traverse the brain in terms of like every time you kept on going down in detail, and you just find new worlds.
Yeah.
And a big part of it was talking about issues of um, how to manage this much data, how to work with other groups when you definitely couldn't move the data around. So they were like building web tools for it, traversing the data. Yeah. Anyway, but Big Brain now, in this eighth meeting, you can see there's plenty of physiological modeling. I mean, this is very much like a very broadly it reminds me of like the full kind of set of topics that you'll see at a human brain mapping, for instance.
Right.
Brain atlases, improving brain simulation, simulation through integration with structure, white matter mapping, so diffusion, um, the and HIBALL, I think is some acronym that relates to like high resolution, maybe again together with I don't know if the acronym's coming off of kind of a particular name in diffusion imaging. Uh, um, but dimensional perspectives on multi-scale cortical organization, just, I mean, it just goes on and on and on. I'm just looking at all the different videos from Big Brain Project YouTube channel that dropped yesterday. Um, you can give yourself, a real kind of perspective on all things brain imaging,
Right.
all topics brain imaging related. So I know it's got a big Ulick focus. Ulick is a number of things. One, it's the supercomputing center in Germany, but it's two, it's also the current head of the the second version of the Human Brain Project. Um, the leader is now Katrin Amund, and she worked closely with Carl Zillis, and who's passed, I think maybe a decade ago. Yeah. Anyway, a while ago, um, and maybe 5 years ago. But anyway, she's now the head of the what is now eBrain, I think. I think is what they call it. Yeah. So she's on. Yeah, but this is the second generation trying to learn from the mistakes of the first, in the sense that people weren't necessarily happy about how that €1 billion were spent,
Oh,
or what they got for it. Yeah. uh, um, and 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 to some degree, yeah, it was like the brain imagers. The brain imagers won. I don't know if that's one way of kind of seeing it. Is that like the first generation was really good for the computational neuroscientists,
yeah.
potentially, and the uh, um, and because I see a lot of initiatives in Europe in terms of trying to be more translational, or certainly start to walk back some of that that original direction to building out kind of fundamental research in areas that hopefully are closer to topics that can be um, I almost want to say commercialized.
Yeah.
But there is a European meeting where I forget what they call that particular meeting, but um, they would like to see something that they're not funding come out of this.
Yeah.
That could be, even better if it's clinically relevant. Brain innovation. Yeah, I know it's a crappy. It's like Brain Innovation Days is the European meeting.
Uh,
There is actually a company called Brain Innovation that's been around for a long time. That's um, a famous researcher in Maastricht runs that company. Anyway, I'm blanking on his name right now. But great set of talks, right?
yeah.
And yeah, can't say enough about it in terms of, there's deep learning examples, um, all sorts of things, and again, I've got to try and make the time to go over this, because again, it's a really nice. It's like yeah, it's all right. I didn't finish that. Ulick is one big part of this. The other part of this is McGill.
Okay.
and and I should say, in particular, Alan Evans, who's the kind of yeah, just a big reason why McGill is the center that it is, in terms of having a big software group, obviously having lots of big data collaborations, and and then just having a bunch of top researchers. But okay, yeah, and there's even a talk here on Big Brain, the McGill multimodal data ecosystem. So right. Oh yeah, and look, introduction. Yeah, HIBALL introduction by Katrin Almans and Alan Evans. So um, a hell of a lot there. I think I dropped a video on Neuro AI special lecture.
Okay.
Because I think Rish or someone had said, "Hey, do we have a Neuro AI interest group
That
or
was
something?"
that was Rish Bosch.
Yes.
Yeah.
Okay. And anyway, that was there. Um, so yeah, a lot of good stuff. And then well, don't let me, if you've got things, I can drop links to this. I feel like I've talked for a long time, but
Yeah. Well, I mean, I think we have a lot of this is a lot of stuff that we can go through, or people can go through. Yeah, definitely drop the highball link in the. I don't know which
oh yeah,
channel that could be. I mean, it could be brain
yeah.
organoids.
I
It could
guess
be.
neuroscience networks. I
Yeah,
don't know.
yeah, neuroscience
Um,
networks.
I, I just wanted to the other one is the Global Brain Consortium,
Okay.
and just pointed out it's globalbrainconsortium.org.
Yeah.
uh, yeah, at least they made the URLs easy, and um, the so celebrating 100 years of EEG, right?
Yeah.
And Hans Berger. There's some interesting videos that you can find at the Mind Brain Clinics in the Netherlands. They did a bunch of history. You can check on Wikipedia too. It is kind of fascinating, kind of the first 30 years of EEG in terms of who was doing what and
Yeah.
with what. But anyway, a lot of big names. We talk about brain imaging, and what I'm kind of emphasizing is actually MRI and PET, and those kinds of things. Electrophysiology, and if you will, non-invasive electrophysiology. So not doing brain surgery has this is kind of the focus, and I think it's great that the opening remarks are from Pedro Valdez Sosa, who's the head of the Cuban Neuroscience Center. And for those who don't know, Cuba, because of our embargo and technology, and because of its emphasis on the medical sector and producing lots of doctors, they have one of the largest corpuses of EEG data in the world,
Wow.
that from all their people,
Yeah.
and uh, that, and the fact that because Cuba was kind of pushed into the Soviet realm, people of Pedro's generation are all Soviet trained mathematicians. So they're all super excellent in computational modeling, but they figured out everything on paper because they didn't have access to our kind of computers. So just
Wow.
to finish with that.
Yeah. Yeah, that's great. Yeah, thanks for the discussion on that. And the Big Brain Conference looks interesting, and highball. And all right, well, let's move on. I don't know if Jesse had anything you wanted to say, or
I can briefly. This is more just like a teaser thing. I missed some of what you were recently saying. I had to attend to something, but those events sounded, good. Basically, I'm really currently intrigued by a question space, I suppose.
Okay.
And it's weird because we've talked about like complexity. We have like a complexity in something curriculum, and we've mentioned this interface to countless times. We've mentioned Complexity Explorer. We've mentioned all this stuff, and I don't know if it's just because I'm very naive and uninformed, which I think is the case. But seeing David Krakauer's work and recent work has been very interesting in a way that I think I need to. I don't know if I want to call it a project, but there's a definite set of questions that I want to investigate relative to his work, relative to what he's been doing at the Institute and where he's going. And basically, like I don't really know if controversy is the right word because it sounds a little more dramatic than I intend. But I- um, it's sort of this space between what is he doing with complexity science or what he calls complexity versus the institute, and where is it relative to sort of what people are doing with complexity in general? Because like I don't really actually remember, or at least I don't think I. If you ask me what is Bradley's or Morgan's take on complexity science, I wouldn't be able to say very well. Like it's like it's something that you talk about or care about in some ways. But like I don't have nuance in that discussion to say, well, I think complexity should be this or not this. I think this is the behavior of where complexity science or theory can work or not. I don't know. Like I feel informed, but like I suddenly feel very superficial about my information and depth. And there's certain things that I haven't heard before, and maybe because I haven't been paying attention to them. But there's certain things I haven't heard before about what David Krakauer is trying to do that feel to me very interesting, but also I don't yet know. It's something that I have to much more deeply understand. Because some of the recent things that I've heard, and there is this new book out, which is, I don't really know if it's a new book so much as a collection of older papers and stuff, and more streamlined. The complex world is an interesting thing, but he's starting to develop this thing like teleonomic matter. Like, what does that mean? And making complexity science about that to me. And at first glance, that's like, okay, that's not what I originally was like. That wasn't um, complexity science to me. But I don't know. Like I never really had a great grasp of it at any rate. But the angle the vision that he seems to be outlining seems very interesting to me. Even if it's something that I think is potentially maybe not maybe incomplete isn't the right word, but more like it could be something I'm interested in really pushing forward, but I don't know yet. Like I feel very um superficial. So I'm trying to find some of his stuff and the conversations. Like there's a conversation with him on Mindscapes, talking to Sean Carroll, Mindscapes, the podcaster guy, who I think is also actually at SFI. And their conversation's great so far because Sean is coming from a bit more of a physicist, classical physicist background, and he's does a lot in that space and is very accomplished, but is more as a conventional, um, that approach. And him probing David about where what is he doing with this stuff, and even him being at the institute himself, kind of seeing where it goes, is a very interesting conversation relative to this too. So that's one thing I really want to dive in deeply As we talked about last week, I think Bradley went, did a big overview of his presentation about complexity, and then it dovetails a lot into the teleology paper for me. Like going back and reading that teleology paper has been very interesting, even if um, it's a really interesting space for me right now, at least for my mind, to be to looking at the 1943 paper in all of its like profoundness and also like the simplicity of things at this time too, relative to what like 80 years later, where like Krakauer is seeing stuff. And I'm just there's some I don't even know necessarily to say what I don't have greatly defined questions, but I know I have some very specific questions that I may try to turn into. I don't know if they'll be like a paper, but I want to do some writings about the space because I find this to be very, you know, maybe useful for some of my overall aims, like things I want to see changed or done, or like we talked about like new kinds of science, both, yes, the Wolfram book, but like doing science differently and stuff for a long time, in this group and other things that I'm interested in too. So it's sort of like where I'm theoretically, like idea wise at a high level, it's appealing. Like in terms of actually developing like theory and tools, um, I don't really know. Like I don't know yet, and it's interesting because it's a different layer of questions and curiosity on somewhat I would say familiar, but like distantly familiar material that's come up. Like I feel like complexity is this term that's just I actually referenced somewhere when I was talking about this elsewhere. It's like, a long time ago, I was like, what happened to cybernetics? And I actually feel a little bit better about that question now. I know where it went now. Like, I know what happened to it. Because when I first came to it, like, I don't know, almost 10 years ago, and I just saw this like kind of random YouTube video at the time from someone, and I went down this long path, and I didn't really find anything, but then I've done so much stuff with it. Like, I know about it, but it's kind of a similar spark of, you know, what is there more within the arena of people trying to do complexity stuff than I maybe understood or like discredited or didn't appreciate fully as sort of the highbrow way of saying it, I suppose. But I don't know. I'm just very curious about that space, and I look forward to talking about that more. I posted something in the Slack about like one of Krakauer's papers about like machine learning stuff. But I'm really interested in sort of his teleonomic matter approach and what that entails for um, potentially doing science differently or having a different tool set from things that are not purpose related and that's part of why like I went through the paper in our discussion, but also like I want to write something specifically about the paper, the 1943 paper, and I kind of did some big whiteboard thing about it that'll um, I'm not going to show it right now, but like there's some stuff I'm doing already in that, and I want to just keep that going. So um, I don't know if either you have anything you want to say about your take on the state of complexity science or some. We don't have to go into it deeply right now.
Right.
But like, any like generic advices or things like, we talked about this or we're in this conversation. You're welcome to that. But otherwise, we can move on to other things too. I don't have like
Right.
any questions outside of a vaguely stated interest at this time.
So yeah, I'd be very interested to see the whiteboard and what that it has on it. Like, because I'm interested in that paper was also very interesting to me in terms of like how do we approach, um, cybernetics, but also like how do we approach sort of behavior versus other things like development and evolution, and how does feedback really factor into Like, what are the what does feedback lead to in terms of behavior, and not just like human behavior, animal behavior, but it's like systems behavior. So yeah, but I guess my other question for you is like, what happened to cybernetics? You said you had the answer.
Okay, thank you.
Oh,
I'm sorry. What was the last bit? I
what
missed the last bit.
happened to
Sorry.
cybernetics? You said you had the answer.
Oh, well, it things happen to it.
Thanks.
But at the very least, I kind of see why it went the way that it did.
Right.
You know, it it it's kind of actually interesting because maybe it's just because I'm more in the. It's so weird because it's like now that I know Michael Levin and what he like that he references the teleology paper
Yeah.
and that he's doing it. Like seeing people contemporary people do the thing helps at least it the personal the affective sense of oh, this is old as hell. Nobody really cares about this. Like, what happened to this term that was really popular and like cybernetic organism terminator, like all these weird uses. It's such a term. The thing, I guess, in similar ways, but like culturally, the cybernetic and cyber this and cyber that has its own kind of. I use the word vibe, but it has its own like the word itself has so much loaded into it. Complexity, I guess, does too similarly, but it it feels I don't know. It feels different somehow too. Um, but yeah, seeing like the 1940s, reading enough of Norbert Wiener to see his take, knowing there's different takes, and seeing kind of I guess you could say natural development of other stuff. That's been nice to see. Like I don't really know what to call that learning experience. I guess it's sort of the answer to the question, the long answer to the question of basically what the question's really like, what did people trying to do computing and control and communication and information, what do they do in the last, 80 years? That's kind of what the question really is. Um,
Yeah.
and then you got the wacky stuff. So yeah.
Well,
um, but but it, it's definitely some things ahead regarding maybe even competing. I might do some if it gets if a potential direction would be trying to do some actual comparative. I don't know if comparative analysis is too formal, but between take some complexity and even seeing like I looked at something like Complexity Hub recently about like we're trying to do problem specific groupings of researches instead of domain, tended by domain. Like, okay, that's cool. What does that really mean? Or there's like the New England Complex Systems Institute, which I've heard a few things about, and attempted to do their summer school or some winter school a long time ago, and I've heard different things about what's going on there. So we'll see. It's a fun space right now, but that's all I got for it.
all right. You said something about a school of 1,000 complexities or something like that. What was that?
Oh, New England Complex Systems
Oh,
Institute?
right. Okay, that's what they're doing. Okay.
Probably, yeah. I don't know what else I would have said, but yeah. Oh, Complexity Hub too. This is something I mentioned.
Okay,
I'm
Complexity
not that
Hub.
familiar with either of them. Well, sort of, but we'll see.
Yeah, there are these other complexity like resources and places like Santa Fe is just one school of thought. Nexi is another school of thought. I mean, they do a lot of stuff with networks. And then Complexity Hub, I think, is like out of Europe, or there are people in Europe doing stuff. And so, like, there are all these different places where they have different schools of thought on what complexity is and what is involved. And so, I mean, it's a very, I think, very fertile ground to kind of lay down your marker and say this is what complexity is. I guess anyone can have their own theory, but like there are always these different schools of thought where people are bringing in different tools. Some people are more focused on networks, some are on dynamical systems, some are on like these sort of postcursors of cybernetics. So that's good that you're thinking about that. I think it would be great to kind of maybe turn that into something, some paper or presentation. So more on that later. Thank you, Jesse, for that. Okay, let's get on with, I wanted to present this article. So this is from the Transmitter. I think I mentioned this last time. It's like a new sort of place on the internet to find neuroscience takes and things like that. So this is
Simon's Institute.
Yeah, Simon's Institute. Yeah.
Simon's Foundation. Yeah.
Or yeah. So they have this. I guess that's a blog or a magazine online. So this is Mark Humphries, is a neuroscientist, and this is about neurocoding. And the title of this article is "Averaging is a Convenient Fiction of Neuroscience." So, we talk about averaging and mean field models and things like that. And it's very easy to work with those kind of things. But in fact, the brain is not like a mean field model. It's not like an average system. If you average things out, sometimes you can, filter out noise and get sort of a good working answer. Sometimes averaging actually hurts you, however, if you're dealing with these non-uniform systems and you have this, and this was a theme in cybernetics, I think, as we talked about on Wednesday, that there's this aspect of how people will normalize things to averages or to normal distributions, and in the brain you can't necessarily assume that. So this is the sort of the theme of this article, and the subtitle is "But Neurons Don't Take Averages. This ubiquitous practice hides from us how the brain really works." So again, this is a nice take. Mark Humphries is the chair in computational neuroscience, University of Nottingham. So this is basically this is the diagram that kind of explains this. This is something he's calling mathematical masking. So you see all these diverse signals coming into this box, and it comes down into this box, and it like forms this nice, neat sine wave. And then it leaves the box as diverse as it came in. So this box here is just basically taking an average of everything. And it's producing this nice sine wave, but the problem is, of course, is that that's just reducing perhaps all the information of those signals down to this one neat little signal that we can measure. So, I mean, we have signal processing techniques. We have other types of techniques that allow us to get information out of a signal. But still, the assumption, of course, is that individual neurons, you're doing this sort of averaging, especially when you're averaging neural activity over trials or over neurons, and you're losing a lot of sort of information about what's happening in the brain. Or sometimes you're losing information about edge cases, or sometimes processes will have a long tail, like an exponential function, where there's a lot of information in that tail and you're just basically chopping it out and working with the average. So this is one of the problems with, some of these normalization techniques that may make our job easier in the short term, but then in the long term, it gives us this model that we would be better off not doing. So this kind of starts off: at any social gathering of neuroscientists, the conversation can turn to what's holding back the field. Funders, some grumble, lamenting the amount of money thrown at microbiology instead. Journals, others chip in, browsing at the gatekeeping editors. The tyranny of old timers, some newly minted print PI often mutters, cursing the difficulty of challenging entrenched ideas. I say averaging, and everyone moves slightly farther away from me down the bar. But really, it is a problem. Averaging is ubiquitous and hides from us how the brain works. So basically, from his perspective, you want to understand the signals sent by neurons. These are basically encoded in spikes, and this underpins the brain's functions. And so to understand, say, how we make a decision, many argue we need to understand the spikes that underlie it, how they convey information about the options available, how they convey the process of a decision between those options, and how they convey that decision into action. Averaging is everywhere in our attempts to understand the spiking of neurons. A good example is that fundamental workhorse of sensory neuroscience, the tuning curve. Imagine that you want to know what frequency of a sound a neuron most prefers. You play that neuron tones in a range of frequencies and count the number of spikes it emits for each. So you have this, you're kind of taking the spike, you're segmenting out the spike, and you're counting these in a range of you're counting the number of spikes for a range of frequencies. You repeat that a bunch of times, average the number of spikes emitted for each frequency, and you've built yourself a tuning curve from those averages. So this is a kind of plot that tells you the average number of spikes the neuron sends for each frequency. So you're basically taking each frequency band and you're getting an average of number of spikes for that frequency band, which, is, you'd think that would be reasonable because you'd have variation in terms of, how many spikes are sent at each frequency. But, this is something that, again, if it's normally distributed, that's fine, but maybe it's not normally distributed within that frequency. Maybe there are things over time that are, aberrant from that average, or, basically it's not a normal distribution within different frequencies. So for low frequencies, it might be a normal distribution. For higher frequencies, it might be an exponential distribution. And it gives you this range of properties that can't be measured easily with an average. So it may well show you that the neuron sends more spikes on average to 100 hertz tones than to 10 or 1,000 hertz tones, suggesting the neuron is tuned to that specific frequency of sound. Okay. The natural extension of this idea is to look across time, creating a peristimulus time histogram. So again, this is another histogram type model where you're looking at some average number of spikes a neuron sends just before and after some significant event. So you want to know like the preparatory aspects of it, and you want to know the consequences of the event. And so you want to see, if an animal repeatedly gets a reward, for example, we look at how a neuron responds to that reward by seeing how many more or fewer spikes it sends on average after a reward than before it. So neuroscientists use averaging for good reasons because it reduces the data that they're working with. It gives you these convenient, neat figures that you can put into a paper, that you can communicate the idea reliably so I can understand it. So, if I have like a graph, again, I might want to take my signals, put them in these bins, different frequency bands, and find an average value and compare the average across these different cases. So this is my mean, these are my frequency bands. And I can make this comparison, right? But let's say the underlying distribution, we want to kind of think about what that is. So for A, we might indeed have a normal distribution, which is sort of a bell curve like this. This is the mean, the central tendency. This is the standard deviation here. And you've described most of the cases that you're encountering in A. So the average makes sense. The average describes something significant about the signal. But let's say that in C, which is maybe a little, the average is a little bit higher, but the structure of the signal is very different. In C, it might be a multimodal signal, something like this, with maybe a long tail at this end. So taking an average, might end up being here, which then the standard deviation would be like this. And it doesn't really describe this underlying function at all, because first of all, there are essentially two means, first of all, that are interesting. So you can maybe report the average of those means, but there are two distributions hidden in here. And then there's this long tail that we can't describe because we've kind of eliminated all those data. So you see that it describes A very well, but C very poorly. And yet the average looks like it's about the same. And even if we do like a t-test between A and C, we might get like something that's not significantly different, but it actually is significantly different in terms of the underlying distribution. And so this is kind of what he's getting at, which is that, we use sort of mean values or average values as the sort of summary of events. And you can't always say that that's a good summary of events. Sometimes it's not a good summary of events. So averaging over time hides what a neuron actually sees, what it actually gets to compute with. So it might be computing with this versus this, and an average won't tell you the difference in that. It hides it. So, we use this as a matter of convenience. Neurons also typically emit different numbers of spikes to the same event. So only by averaging over many repeats of the same event can we seemingly extract the reliable signal that the neuron uses to encode it. So there's a lot of variation in terms of if I have some event, like if I get a reward of juice from a juice box every time I select a target, if I'm a nice monkey and I do my job in my experiment, I get this reward. And every time I take a sip from the juice box and get that reward, there are a different number of spikes that are emitted. So it's kind of hard to say, maybe like sum the number of spikes, because it's going to be a different number every time for every event. And you might think that, maybe these events are treated differently by the brain when in fact they're basically the same response. It's just there's some variation there. So we use the average to sort of gloss over a lot of that sort of variation or noise. It doesn't matter so much in terms of what the actual response is. So on the other hand, you can have these kind of responses that are multimodal, or these kind of responses that are qualitatively or even quantitatively different, and they can't be described with an average. So averaging undoubtedly helps us wrap our heads around the complexity of the brain's activity. We even use the average response of neurons as the starting point for some of our most sophisticated analyses of population activity, such as the variance of principal component analysis. So this is a link to an eLife paper, Demixed principal component analysis of neural population data. And this is, of course, a type of PCA that they use for getting at neural population data. So there are a lot of different types of analysis of variation that you can use to get signals out. And so this is actually one method, such method. So in this case, you have, you're looking at the complexity of single neuron responses, and those can obscure what information these areas represent and how it is represented. So they're using these dimensionality reduction techniques. In this case, demixed principal component analysis decomposes population activity into a few components. In addition to systematically capturing the majority of the variance of the data, DPC also exposes the dependence of the neural representation on task parameters such as stimuli, decisions, or rewards. So this gives you this sort of model for dealing with different types of data. So This kind of goes into these kind of problems with using averages, using different types of dimensionality reduction, even because the basis of dimensionality reduction is that we're finding these components that describe the variation. So, it's maybe in some ways it's a similar problem. So this kind of goes through some of the things that people have done in the field. The final answer eludes us. On single trials, some neuron spikes seem more step-like. Other neuron spikes seem more ramp-like. So they're different types of spikes. And if you just count spikes, you're going to miss that variation. But irrespective of how many neurons increase their rates or how many stepped or ramped in a single trial, the problem of averaging is clear. Many single neurons do not look like the average ramping response and do not fit theory based on it. So, you might think that like counting spikes or averaging spikes will solve your problem, but even then, not all spikes are equal. So if there's an averaged ramp response that we're looking for, and we assume that every spike does that, there are other types of spikes that we're kind of filtering out, and those may actually be important in the at least in terms of getting some interesting information out of the experiments. It doesn't match our overall theory. So sometimes when we do theory building, we kind of build theory on these archetypes or these averaged ideals of what a system should look like. So we might take build a theoretical model where we assume that all spikes are sort of similar and that you can do this method and you can get down to an answer that's very clean and neat, and it fits into sort of a theoretical statement and that sort of thing. But that's actually maybe not the best way to approach experimental data. So whenever most of us average neural activity over trials over neurons or both, we're implicitly assuming that the resulting signal is what the rest of the brain sees. We're hoping that all the variation of individual neurons is distributed across the whole population of neurons in a way that their aggregate moment-to-moment signal is approximately the same as the signal we get by averaging the output of each neuron. It's weird that we don't know if this assumption is true. Averaging is ubiquitous, central to our tools, and part of the language. But we know in our hearts that as a matter of convenience, an easier way to think about the brain. Indeed, averaging spikes may just be an accident of history rather than a rational approach to understanding the brain. So, again, it's at the heart of kind of what kinds of theories we use to do these kind of analyses. It's a very simple language. It's a clear language people can understand, and yet it may be very wrong because it does cut out a lot of the complexity that we need to know. And so this is an interesting point. Before computer-generated graphics existed, a simple histogram of a neuron's averaged response was the simplest thing to draw. So that's very interesting that, and that goes back even into the history of complexity theory, that a lot of these analyses in complexity theory weren't possible necessarily before high-powered computers were available. We couldn't explore fractals, for example, until we had these kind of high-powered computers that could simulate things and generate the analyses we needed. And so you could do things on paper, but it was hard to do. It's hard to describe things. So this is interesting that computing actually was serving traditionally as a barrier to a lot of this. And so this just an aside there that might be useful in thinking about alternatives to this. We now have the tools we need to find out if averaging is showing us something about the brain signals or is a misleading historical accident. And so that's basically the take-home message of this. Now Morgan is going to say something.
I was just gonna just to add to that you talk about histograms and the the text that is kind of seminal is Tukey's exploratory data analysis.
Yeah.
Right, so, like 1960s.
Yeah.
That seem right? Anyway, it was, you know, he was at Bell Labs, right?
Yeah.
And um, you know, that one is the first one that, you know, he has all these kind of like simple prescriptions, but forgetting at these kinds of things where it's just like new representations of the data that give me insights,
Right.
right? As opposed to just the kind of the parametric tools that you know, Fisher, Pearson, others um, had given us. And it was profound. It was profound even before computer graphics.
Yeah.
Right. And then you know, yeah, and like the end of that being kind of like, you know, um, like UMAP and stuff like that, like,
oh, yeah.
right? Yeah, but they really do build on a bunch of kind of super basic. I mean, you know, the kind of Tuft visualization of data,
right.
kind of stuff that there's, yeah. I wanted to say I dropped a link in open chat forum on Slack that gets at Humphries. Uh, yeah, click on that link from EEG Lab.
Okay. Yeah.
And scroll down a little, and they call these ERP images. So there's you know, in a sense, this is what the data looks like, you
Yeah.
know, as collected, but then keep going down, right? And you know, so there's this, and then if you keep scrolling down, then they sort the trials, and then these kind of new relationships are coming out from the way that they're sorting them.
Oh, yeah.
Right?
Yeah.
It is yeah, and then there you go. You know, the I don't know if you know. So it's basically, imagine an EEG trace is actually just one line of this plot, right?
Right.
Like turned on its side and then color coded instead of being a squiggly line, right? Like the squiggly line at the bottom is kind of the grand average, but the each one of those is a squiggly line. It's, you know, in this case it's POZ, right?
Right.
Or is it F? I can't see.
POZ.
But
Yeah.
In the like late 90s, I mean, you know, again, like when I started in EEG, everybody was doing ERPs,
Right.
which is averaging.
Yeah. Yeah.
And of course, but I was coming out of the I refused to do stats in the psych department. I wanted to do stats in the math department.
right. Yeah.
So I had done stats, you know, with mathematicians, and we're using R, you know, which is like the actually I think I originally used S, which again is the actual language that came out of Bell Labs and
Right.
was commercialized, right? And then R is the GNU version of S. And you know, a big part of working with the data, certainly the first thing we learn is not to apply these models, but the first thing you see is what tests should you do to see if these models are appropriate.
Yeah.
And of course, you know, and so, you know, looking for ways to determine kind of the distribution, underlying distributions and things like that, non-normality measures and homogeneity of variance measures and things like that, right?
Right.
And of course, as soon as you start applying any of those things to actual EEG data, or ERP data, it's just like, oh my lord, none of these assumptions hold.
Yeah.
like, like, and so it was, again, this is why it was such a pleasure to have worked with Carl Pribram, because Carl was retired, or emeritus when I met him, and I'm just trying to get across like how old he was, and he was a brain surgeon from the 30s, right?
Oh yeah.
He knew Walter Freeman, the one who did lobotomies,
Right, yeah.
and things like that. He was totally against them. He was aghast. Uh, um, um, but what I would say to him, so he can tell you everything about the history of EEG data analysis, because he was like in Boston with the first computer,
Right.
like literally the first computer, and so he was quite rightfully pointing out that like they had to do averaging for ERPs in the 60s, because that was all that was kind of algorithmically computable because of memory requirements.
Right.
and that it's a great example of just a field getting into I mean, I don't want to, like, rut's not the right thing, but it's like there was a reason to do that at the time, that was a semi-appropriate transform, or denoising,
Right.
right?
Right.
And it's not like there wasn't some results from that, but 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 it became this it just it was like, well, we've got to keep using this hammer.
Yeah.
And the experimental complexity, or the ability that we had, and the new amplifiers that we had, and obviously high density EEG also changed things, right? Because certainly my first paper, or my first poster, um, on on anything was multi-way data analysis of high density EEG studies, and it was an SVD based approach, but it was essentially a tensor analysis of high density EEG data, because I had space and time, right?
Yeah.
And I had space, I had time, I had trials, and I had subjects, and so yeah, it was, together with Joe Dean. Joe Dean was the last author, and that poster was presented in the World Trade Center.
Oh well, yeah.
Yeah, because it was it was cognitive, because I'm old. It was Cognitive Neuroscience Society, 2001.
Oh, okay, yeah. That was earlier in 2000.
So it was the summer. It was the summer before.
Wow. Okay.
September 11th.
Yeah.
Yeah. And but so I was just checking out this demixed principal component analysis, and again, it's so I kind of came up in EEG as EEG lab kind of came up too, right? Because it was actually in the 90s, it was called ICA lab.
Yeah.
Or no, it was called ICA toolbox.
I see it. Okay.
And he had a bunch of features, and I can remember was it Mike Warden? I think it was Mike Warden. I remember him coming up to my poster at at CNS and saying like, he was checking out, my multi-way analysis, but he was just like, I see you used my plot figure tool from ICA Toolbox. So I was like, oh yeah, yeah. I forget who that was now, but anyway, but these ERP images were also really interesting. I mean, it was actually like at the time I was the software engineering manager at Electrical Geodesics, right? So it's like this high density EEG company. These ERP images I was actually also using across channels. So there was what we called a synoptic display, and those were really interesting too in terms of the spatial connecting them in that way to kind of create those same kind of plots, those color plots, but they represented space. It was also really interesting how your visual system was very well suited to bring out structure from that.
Oh yeah.
And like when you saw something in that, like it was real. It wasn't necessarily easy. As you see in the ERP images, you kind of have to take a slice. I mean, you take a column, and you see this in the ERP image. But you take a column and then you turn that into a scout topography. Anyway, it's this particular this little transmitter article brought up a lot of memories for me.
Yeah.
But I see. I mean, I think Mark Humphries is like probably more used to kind of invasive recordings from animals.
Yeah.
But the everything you see in the EEG lab ERP images is very similar. It's very similar progression through Scott McCaig's like problems with ERPs, right? Event related potentials. This averaging. And trying to find new ways to examine the single trial structure.
Yeah.
And then he did another version of this that's so you can take the time and you can do a short time Fourier or wavelet transform. And EEG Lab did a wavelet transform and create joint time frequency plots.
Right.
So this is again a way of making your data sets much bigger.
Yeah.
And we also again, like, you got to remember, computers in the 90s weren't exactly ready for 256 channel 1,000 samples per second. Like we would hit problems with 2 gigabit file sizes on 32-bit computers. Anyway, so the joint time frequency was another kind of, in a sense, pioneering work that came out of EEG Lab in terms of what they called event-related spectral perturbations, which again was getting at this what they were seeing in the joint time frequency. Perhaps average, but certainly they tried to get at the single trial. And again, like ICA, which is is similarly a kind of fancy PCA, right? And the dimensionality reduction that you choose, the number of components you choose, right? You could use this for denoising, or you could use it as they do in this demixing principal component analysis to try and get at kind of greater, more complexities of the underlying data.
Right.
And you know, this most certainly will eventually hit something like partial least squares, where you're getting at you're including the design together, you know, in the PCA. And you know, it's another technique that is widely used to kind of bring out with principal components to bring out the kind of underlying the latent structure that is most correlated with your design matrix. Yeah.
Yeah.
But super cool stuff.
Yeah, great stuff. All right, so I'm gonna go. Let's see. Share my screen here. So yeah, it was a good article. They talked a little bit about you know, some of these problems with averaging. Um, this was about a paper here where they looked at this, you know, response to moving dots in, like I guess a macaque, and they found that there was a great diversity of activity in cortical neurons, that they behave in all different ways. And there was an argument that raged back and forth about, well, how well we can tell during a single trial if a single neuron steps rather than gradually increases its spikes. So this was, I think, the paper that they're referring to here in Science. Single trial spike trains in parietal cortex revealed discrete steps during decision making. So this is actually, I think, in humans. This is actually, I think, they say a better way to explain neuronal activity. A brain region called the lateral intraparietal area, or LIP, is involved in primate decision making. The dominant model to explain neuronal firing in LIP assumes that neurons slowly accumulate sensory evidence in favor of one choice or another. So you're linking it to sort of this behavior cognition that happens as a result of the spikes. Latimer et al. Hypothesized that neurons, instead of exhibit rapid steps or jumps in their firing rate, reflecting discrete changes in the animal's decision state. They recorded from LIP neurons in macaques performing a motion discrimination task. LIP spike trains in most cells involve discrete stepping dynamics rather than slow evidence integration dynamics. So you can see that there's this sort of variation in interpretability of these experiments based on the underlying theory, based on the underlying statistical methods that are used. So that's kind of finishing up on that paper or that article. One thing, I guess I'll do one more thing before we end for today, and that is this set of articles. So this is on self-replication and some neuromorphic computing stuff. So hopefully this kind of fits together, and we'll go through it. So this is an article from, I think it's from 1998. Yes, it's from Artificial Life Journal. It was like the 4th issue, or the 4th volume. And this is by Moshe Sipper, who's a complexity theorist. And this is on 50 years of research on self-replication. This is an overview of the type of self-replication work that von Neumann was doing with cellular automata. So he had these self-replicating structures that were basically the cellular automata that would exhibit sort of a developmental stage, and then they would self-replicate. And so this is like thinking about this from the standpoint of 1998, thinking back 50 years, which was 1948, I guess, and thinking about von Neumann's work and its legacy. So this is the abstract. The study of artificial self-replicating structures or machines has been taking place now for almost half a century. This is again 1998. My goal in this article is to present an overview of research carried out in the domain of self-replication over the past 50 years, starting from von Neumann's work in the late 40s and continuing to the most recent research efforts of 1998. I shall concentrate on computational models, that is, ones that have been studied from a computer science point of view. So these are not like, computational neuroscience theoretical models. These are really computer science oriented models, be it theoretical or experimental. The systems are divided into four major classes according to the model on which they are based. And the four classes are cellular automata, computer programs, strings or strands, or an altogether different approach. So you have ones that are based on cellular automata, which are the standard ones that von Neumann worked with. You have computer programs that basically can self-replicate. You have an evolutionary algorithms or an evolutionary computing. You have strings that can be recombined and replicated, or other approaches like an unconventional computing. So he kind of reviews those. With the advent of new materials such as synthetic molecules and nanomachines, which would fall into that fourth class, it is quite possible that we shall see the somewhat theoretical domain of study producing practical real-world applications. So he kind of talks about what von Neumann was doing in the 40s. He was interested in the question of whether a machine can self-replicate, that is, produce copies of itself. So he wanted to investigate the logic necessary for replication, not just the act of replication. He didn't really want to build a working machine at the biochemical or genetic level. So he didn't want to replicate biological reproduction. He just wanted to replicate the logic of reproduction and what a computational system needed to achieve to produce replication. So the study of artificial self-replicating structures or machines has been taking place now for almost half a century. Much of this work is motivated by the desire to understand the fundamental information processing principles and algorithms involved in self-replication, independent of how they're realized physically. So this is like kind of how you could have a system that is totally divorced from reality and how that might want to replicate itself. So, if you had a program in a computer, how would it replicate itself? And what would be the sort of conditions under which it would replicate? And you might think that's a weird question to ask, but really, it's like if you're talking about like a learning machine, or if you're talking about a machine that, or a program that undergoes evolution through an evolutionary algorithm, then that's maybe an easier way to think about it. And it may be a much more reasonable way to think about it because there's an imperative there to do something that self-replicates. So it may advance our knowledge of biological mechanisms of replication by clarifying the conditions that any self-replicating system must satisfy and by providing alternate explanations for empirically observed phenomena. The fabric of artificial self-replicating machines can also have diverse applications, ranging from nanotechnology to space exploration. So this kind of goes through, actually there's a nice map here it's a lineage of works in the area of self-replication. So a solid line in this diagram represents a close relationship between two works, while the latter may be an extension or an implementation of an earlier. So we start with von Neumann's work in the 1840s, and we can see up at the top, and then we go down to the work of Arbib, of Smith, of Codd, of Kemeny, Moore, Jacobson, Morowitz, Penrose, and Penrose. So Arbib is interesting because Arbib is, of course, doing artificial intelligence work. In the 1960s, Arbib has done a lot of really interesting work historically. I think he's retired now, no longer active as a researcher, but having done a lot of really interesting work in AI in the 60s and 70s and 80s. So, of course, the author of this paper is related to Arbib's work. Arbib had an influence on a number of different types of work. And you can see that this persisted down to the era of the 1990s. And so you see in the legend that these squares are cellular automata. So RB pursued the cellular automata path, and that had like some descendants. Programs in circles here. Ratley and Millo, 1972, took inspiration from von Neumann to build out. You have Dewdney, Ray, who developed Tierra, and then John Koza, who developed some things in evolutionary programming. So that was using programs. So this was, of course, evolutionary type programs. Then, of course, you had in the triangle, you had strings, so you had Lang, you had Morris and Veretto. So these were strings, and I guess there were connections there with cognitive modeling, and then other in this shape here, the diamond, you have Freitas Jr., NASA project, Rebec Jr., and I guess these were more of like the synthetic approaches to synthetic life. So, there's a lot of stuff that kind of diverged from von Neumann's early work, and it took different forms. And so that's very interesting, and it kind of goes through all of these kind of areas of work, from cellular automata to, different sorts of universal Turing machines, and sort of the logic of replication. So there are a lot of aspects to this work that, if you're interested in, programs that replicate or systems that have biological properties, learning systems especially, this is something you might want to explore and think about, and maybe follow up in some of these works. So that's that paper. And then this other paper here is from 2020. This is from a series of authors here, Zhang et al. And it's from Nature. And it's a system hierarchy for brain-inspired computing. So the connection here is that we're establishing these kind of models of modeling neuro-inspired or biologically inspired computing, and how do we kind of take these properties of neural and biological systems and build like kind of this framework for understanding these things, both for artificial systems and for systems, better understanding biological systems. So this is where they develop a systems hierarchy. So the abstract here reads, neuromorphic computing draws inspiration from the brain to provide computing technology and architecture with the potential to drive next wave of computer engineering. Such brain-inspired computing also provides a promising platform for the development of artificial general intelligence. But unlike conventional computing systems, which have a well-established computer hierarchy built around the concept of Turing completeness and the von Neumann architecture, so we talked about that with respect to some of these models of self-replication, there is currently no generalized system hierarchy of understanding of completeness for brain-inspired computing. So we don't understand how, say, Turing completeness fits into brain-inspired computing, nor do we have any analogies to the von Neumann architecture. It's in terms of like computational theory, or sort of kind of flying blind. And like the Turing completeness aspect, if you're going to develop a system that is sort of mimics something like a biological system, or mimics a complete computational system where you can perform any computation, you need this aspect of Turing completeness. And so we don't really have that in bio-inspired computing and neuromorphic architectures. We just simply have an architecture that we have to sort of ascribe these computational principles to. This affects the compatibility between software and hardware, impairing the programming flexibility and development of productivity of brain-inspired computing. Okay, so again, brain-inspired computing is great because we can leverage the power of the brain, but to understanding it as a computational paradigm, we're a long ways from doing that, because we don't have these basic concepts sort of mapped to the system itself. So in this paper, they try to solve that. They propose neuromorphic completeness, which relaxes the requirement for hardware completeness, and a corresponding systems hierarchy, which consists of a Turing-complete software abstraction model and a versatile abstract neuromorphic architecture. Using this hierarchy, various programs can be described as uniform representations and transformed into the equivalent executable on any neuromorphic complete hardware. So the neuromorphic hardware has to have these components. You have this so you have a hardware layer that's compatible with a software layer that can perform different tasks or perform different computational functions. And it's not like restricted to only certain functions. You can do any set of functions you can think of. So this ensures programming language portability, hardware completeness, and compilation feasibility. We implement toolchain software to support the execution of different types of programs on various typical hardware platforms, demonstrating the advantage of our system hierarchy, including a new system design dimension introduced by the neuromorphic completeness. We expect that our study will enable efficient and compatible progress in all aspects of brain-inspired computing systems, facilitating the development of various applications. So this is kind of their model here. You have the software layer, the compiler layer, and the hardware layer. And all of these kind of have their own aspects. You have neuromorphic chips as the hardware. You have these different, configurations. On the left, you have the neuromorphic or the brain-inspired computing hierarchy. On the right, you have the modern computing hierarchy. So you can see that on the left, you have these neuromorphic chips. On the right, you have general purpose chips such as CPUs and GPUs. And so what they're doing is they're mapping what we know from a Turing-complete artificial computer to a neuromorphic computer and thinking about this in terms of creating a neuromorphic complete system. So you have the hardware layer where you have the neuromorphic chips being mapped to memory in an interconnection network. So this is very much like the instruction set architecture of the von Neumann architecture in artificial computers. And then you have this compiler level, so you have these analogies here. And then you have the software layer where you have applications, a neural network framework for the brain-inspired computing hierarchy, applications and programming languages in the modern computing hierarchy. So it's a matter of mapping from the von Neumann architecture to a brain-inspired architecture, all the while trying to make this sort of, at the software level, Turing complete, but at the compiler and hardware level, neuromorphic complete. So this kind of goes through some of the aspects of using synapses and dendrites and other things, other functions in neuromorphic computing, and thinking about this as, kind of a model for computation. So you have all these components, you put them together, and you try to derive this Turing complete system. So yes, this is a very good paper too. It kind of links back to self-replication in that, what you're trying to do is you're trying to build these, or you're trying to map between these biological functions and these computational functions and trying to figure out how those things work at a functional level, but also at a theoretical level.
Yeah, it's interesting. Yeah, I haven't seen that kind of discussion around in neuromorphic computing. Again, I want to digest that.
Yeah.
If you've got a PDF, actually, I didn't check. Yeah. Let me just see if that's available from the usual sources.
So, well, I can put the PDFs in the Slack. So.
Okay.
Yeah,
okay.
Yeah.
Cool. Yeah.
Right.
Yeah, it's interesting. I mean, I forget now the exact context of the conversation, but we're still certainly as part of Celsius in like synthetic biology. Um, uh, our ability to get work from biological systems
Yeah.
is still infancy doesn't seem to do it justice.
Yeah.
It is a desired goal,
Right.
and certainly trying to get computing work from biology um, is yeah. So it'd be interesting to see where how much that relates to kind of yeah. I just haven't seen that in the context of like spiking neural network kind of modeling, which seems to be the majority, not all, but the majority of neuromorphic computing kind of work, right?
Yeah.
But it definitely relates to this what I call ORAC, which is the organoid research and augmented computing, where like hopefully and what Thomas Harding and the Baltimore Declaration people call organoid intelligence.
Yeah.
Right. Is like at what point do our biological models become kind of relevant for computing?
Yeah.
Right. And not directly relevant, but just certainly in terms of some amazing biology work, right? Is that it was the Ventnor Institute's minimal cell workshop. and you can see all their videos in terms of the kind of synthetic cells, and well, they're not fully synthetic, right? Yeah, but just the interface of like the really interesting work that is in synthetic bio is its own direction, right? Because like he's very much keeping parts of like a big part of that workshop was which organisms are interesting in this minimal cell project.
Right.
And it seems to be which are good vessels for us to hijack.
Yeah.
And interesting natural organisms to modify and work with. So
Yeah.
anyway, hopefully potentially it will come around to helping us understand how to better engineer biology.
Yeah. All right. I think that's it for today. Thanks for attending, and see you next week. Thank you.
Take care, Brad.
Take care. Bye.
Bye.